So, you've learned all about Riemann sums and integrals as ways of calculating the area under a curve. But let me throw a curveball at you. Let's look at the curve for 1 over the square root of x plus 1. We see the vertical asymptote, so we know the function isn't defined at that point. It's going to infinity. We call that a discontinuity. The function doesn't do normal function stuff at that x value. Like with any other function, we can integrate to find the area under the curve. Generally, though, I want to avoid that asymptote. Say I want to tempt fate, though. I inch my interval closer and closer to that asymptote to see what happens. And something weird happens. My integral doesn't blow up like the function does. In fact, it seems to approach a value. This flies in the face of the intuition we've been building up about integrals. The function itself is blowing up, but the area isn't. To give you some idea why this happens, think about how tightly the function clings to its asymptote. It's so close that going higher by getting closer doesn't add much area. When your integral goes to infinity on an asymptote in the function you're integrating, that's called an improper integral. Now, note that not all functions are going to do this. If you just take a random function with an asymptote, it usually won't grab its asymptote with such a tight grip. Instead, it might just blow up, or diverge. If it doesn't blow up, we just call that converging. The asymptote doesn't have to be vertical either. You can write an integral that grips a horizontal asymptote all the way to infinity and still converge. Take 1 over x squared as an example. If you integrate it from 1 to infinity, it actually has a value. We also call those kinds of integrals improper. Now, as fun as it is drawing graphs and shading them all day, we might actually want to find those values, and whether they converge on paper. To do this, you first have to recognize that you're actually dealing with an improper integral. This is pretty obvious when it's the horizontal asymptote kind. One of the limits will be infinity. You can check for the other kinds by looking for the usual hallmarks of a vertical asymptote. Often, this means looking for places where you could end up dividing by 0. If it does have a vertical asymptote, is that vertical asymptote in your interval? If it is, then you are probably dealing with an improper integral. Once you have a bona fide improper integral, you can integrate it by turning its problem limit into a limit. Basically, we're just going to avoid the problem by replacing the problem limit with a variable, often n, and take the limit as n approaches whatever you just replaced. Once you have your weird limit quarantined, you do your integral exactly as you normally would. Like many integrals, this can take a minute, so pause to make sure you got every step. After you integrate, you'll have just a regular limit, and it works exactly as you're used to limits working. That is, they can converge, they can diverge, and if it converges, that actually tells us the value of the integral. Now, there's a couple of extra details I should talk about before I let you go. Starting with, what happens if your discontinuity is in the middle of your integral area? This can still converge, surprisingly. However, I can't just replace one of our limits with n, since the problem number, the vertical asymptote, doesn't appear as one of the limits. So, here's what you gotta do. Split the integral into 2 integrals. Each integral now has the limit present, so you can use the method we just mentioned on it. Make sure you treat those 2 limits as separate limits, though. If either of them diverge, the whole thing diverges. Another weird case is, what if both ends of your limit are problem numbers? Like, what if your integral goes from negative infinity to infinity? Or between 2 asymptotes? In those cases, you can actually just create 2 separate limits with 2 separate variables and stack them. It'll look a bit weird, but if you focus on one limit at a time, it'll work out. Hopefully that gives you enough to get started. Bye!